Good morning, students. Today we are going to see Unit 5 Memory Management. Myself, Professor Avhad PS, Sri Chhatrapati Shivaji Maharaj, College of Engineering, Nepti, Ahmednagar. So, first of all, what is meant by memory management? Memory management is nothing but it is a task that carried out by the operating system and hardware to accommodate multiple processes in memory. If only a few processes that can kept in main memory, then much of the time all processes will be waiting for input output and the CPU will be idle. So mostly memory management is nothing but simply tasks that are carried by operating system and hardware to perform processes in your main memory. So what are the memory management requirements that we will see? First of all, relocation. Programmer cannot know where the program will be placed in memory when it is executed. So a process may be relocated in main memory due to swapping. Swapping enables the operating system to have a larger pool of ready to execute processes. So from this point relocation we understood that programmer don't know where actual program is loaded in memory, and during execution of that program it will get swapped by swapping concept. Temporarily it is loaded into secondary memory and another access during execution. Memory management requirement. Next point is protection. Processes should not be able to reference memory location in another processes without permission. It is impossible to check address at compile time in the program since the program could be relocated. Address references must be checked at runtime by hardware. So this is another requirement of memory management that provide facility of protection to your processes during process management in memory management. Next requirement of memory management is sharing. It must allow several processes to access a common portion of main memory without compromising protection. Cooperating processes may need to share access the same data structure. It is better to allow each process to access the same copy of the program rather than have their own separate copy. Overall goal of your memory management: require minimal hardware support. First of all, keep impact on memory access low. Third one, keep memory management overhead low, that is for allocation and deallocation of memory. So memory allocation mainly divided into two parts, that is first of all contiguous memory allocation, another is non-contiguous memory allocation. Contiguous allocation. So once the memory allocation allocated, the oldest memory allocation scheme allow when process need to execute. The memory is required by the processor. So process need to execute memory when it is required by processor. This continuous allocation depends on the process. The size of process is compared with the amount of continuous main memory available to execute process. Continuous allocation consists of fixed size partition, variable size or dynamic partition. These are the structure of your fixed size partition, in which allocation table is shown, in which occupied bit, partition size, processes, and that is represented in the form of memory, that is 5K, 8K, 1K. Variable size or dynamic partition. To overcome the internal fragmentation problem, variable size partition are introduced. It allocate the table depend on your dynamic partition or variable size. These are the representation structure of variable size or dynamic partition. allocation table, start address, size, and your process. That is free because it is a dynamic partition. So variable size or dynamic partition, it includes placement algorithm which are used to decide which free block to allocate a process. Recently in previous diagram you have seen the process is free. So these are decided which free block is allocated to particular process which are in running mode. So the dynamic partition or placement algorithm goal is to reduce uses of compaction, that is time consuming. For that purpose, some possible algorithms are referred. It includes first best fit that choose smallest hole. Next, first fit that choose first hole from beginning. Next fit choose first hole from last placement. That we will see later. So variable size dynamic partition placement algorithm. Next phase. It often leads to allocation of largest block at the end of memory. In first fit, favor allocation near the beginning tends to create less fragmentation than next fit. And last one, that is best fit. It searches for smallest block. The fragment left behind is small as possible. Main memory quickly forms holes too small to hold any process. Compaction generally need to be done more often. Next topic or next point in memory management, that is swapping. So normally what is meant by swapping, that we will see. A process can be swapped temporarily out of memory to backing store and that brought back into memory for continuous execution. Simply what happens during execution of your program, your main program is executed from main memory. During that time another programs are residing in memory that are going to be temporarily stored in your secondary memory, or during execution that are going to load it into secondary memory or primary memory. That time for temporary they are stored in your backing store, that is known as backing store temporary, and when particular process is executed, then from that backing store that running process is accessed into primary memory and later that it will be get executed from main memory. That is concept of swapping. For that purpose they use two main important concepts, that is first one backing store, that is already you understood backing store, and second one is rollout and roll in, that is swapping variant used for priority based scheduling algorithms. Lower priority process is swapped out so higher priority process can be loaded into executed. These are the scheme of view of swapping, where your operating system user space main memory temporary that are stored in your swapping, that is particular process, and when that program want to execute from main memory that will get swapping. That is concept of swap out and swapping in swapping concept. Now next point is regarding with your non-contiguous allocation. As memory size increases, problem of external fragmentation increases. So the non-contiguous memory allocation allow a process to acquire the several memory blocks at the different location in the memory according to its requirement. It also reduces the memory wastage caused due to internal and external fragmentation. So recently you have seen non-contiguous allocation provide facility to acquire several memory blocks at the different location into memory as per the requirement. Also it provides facility to reduce memory wastage. That is one of best facility provided by non-contiguous allocation. Two way which allow process physical address space to be non-contiguous. First one paging and second one is segmentation. That we will see later. The process is divided into block, that is pages or segmentation, which are placed into the different area of memory space according to the availability of memory. It increases the overhead of address translation. Need a system to take user virtual addresses and translate into physical address corresponding to the physical memory present. So now we will see the point paging. Paging is nothing but main memory is partitioned into equal fixed size, that is known as a small size. Each process is also divided into chunks of the same size called pages. The process pages can be thus be assigned to the available chunks in main memory called frames. Normally paging is distributed into two parts, that is paging and frames. So a process does not need to occupy a contiguous portion of memory. These are the structure of your paging tables. The operating system now need to maintain a page table for each process. Every process having separate there is page table. Each entry of page table consists of the frame number where the corresponding page is physically located. The page table is indexed by the page number to obtain the frame number. A free frame list available for page is maintained. Logical address which are used in paging. Within each program, each logical address must contain of page number and offset within page. A CPU register always holds the starting physical address of the page table of the currently running process. So presented with the logical address, that is page number and offset, a processor accesses the page table to obtain the physical address, that is frame number and offset. Next point, recently we have seen what is meant by paging. Now we will see the segmentation. Each program is subdivided into block of non-equal size, that is known as segmentation or segment. When a process gets loaded into main memory, its different segments can be located anywhere. As like your recently we have seen paging. When process loaded into main memory, that will get divided into anywhere or any section. Same like that, segmentation also when get loaded into main memory, different segments can be located anywhere. Each segment is fully packed with instruct or data, that is no internal fragmentation. Look here, in segmentation there is no internal fragmentation. So there is external fragmentation, that is it is reduced when using a small size, right? Simple segmentation and paging comparison. First point, segmentation requires more complicated hardware for address translation. Second point, segmentation suffers from external fragmentation. Third one, paging only yields a small internal fragmentation. Fourth one, segmentation is visible to the programmer, whereas paging is transparent. Last one, segmentation can be viewed as commutative offer to the programmer to organize logically a program into segments and using different kind of protection. Example, execute only for code but read write for data. For this we need to use protection bit in segmentable intents. Segmentation with paging, that is multics. The multics system solved problems of external fragmentation and lengthy search time by paging the segments. So solution differs from pure segmentation in that the segment table entry contains not the base address of the segment, but rather the base address of page table for this segment. Now next point that we will see, what is meant by virtual memory. Virtual memory is nothing but your separation of user logical memory from physical memory. It is a simple point, that is, you are going to separate your user memory from physical memory. It contains only a part of program that needs to be in memory for execution. Logical address space can therefore be much larger than physical address space. Allow address space to be shared by several processes, allows for more efficient process creation, more programs running concurrently, less input output needed to load or swap process. These are the structure of your virtual memory, that is memory generated for temporary. In virtual memory, virtual address space, that is logical view of how process is stored in your memory, that is usually start with at address 0, that is contiguous addresses until end of your space. Meanwhile, physical memory organized in page plane. MEMU must be mapped, that is memory management unit must map logical to physical. Virtual memory can be implemented by demand paging or demand segmentation. These are the virtual memory that is larger than physical memory, which consists of virtual memory, memory map, physical memory, and that is final backing store. Demand paging, next point. Bring a page into memory only when it is needed. That is nothing but your demand paging. As per requirement of your process, that are going to be that page is loaded into your memory. It includes less input output needed, no unnecessary input output, less memory needed, fast response, more users. Page is needed reference to it, that is invalid reference about not in memory brings to memory, that is similar to paging system with swapping. Lazy swapper, that is never swap a page into memory unless page will be needed. Swapper that deals with pages is pager. Valid invalid bit, with each page table entry a valid invalid, that is present absent bit is associated. Valid in memory, invalid not in memory. Initially valid invalid bit is set to I on all entries. During address translation, if valid invalid bit in page table entry is page table I, that is invalid is page fault. These are your virtual memory mapping example, how memory is mapped. Page table when some pages are not in main memory. These are the structure where logical memory, page table, physical memory and backing storage is represented. Steps which are handling in page fault, that is loading memory, operating system references, restart instruction, reset page table, try physical memory, bring and missing page. Steps in handling page fault. If there is ever a reference to page not in memory, first reference will cause page fault. Second, page fault is handled by the appropriate operating system services routines. Third one, locate needed page on disk. Fourth one, swap page into free frame, that is assume available. Reset page table, that is valid invalid bit B. Restart the instruction that caused the page fault. What happens if there is no free frame? In page replacement, find some pages in memory but not really in use, swap it out. Need page replacement algorithm. Performance want to algorithm which will result in memory number of page fault. Same page may be brought into memory several times. Steps in handling page replacement. Find the location of desired page on disk. Find a free frame, that is if there is a free frame, use it. If there is no free frame, use a page replacement algorithm to select victim page. Bring the desired page into free frame, update the page and frame table, restart the process. There are some page replacement algorithms which are mostly used. First is first in first out, that is FIFO. LRU, least recently used. Last one is optimal page replacement algorithm. First of all, we will see first in first out. It treats a page from allocated to a process as a circular buffer. Sorry. When a buffer is full, the oldest page is replaced, hence first in first out. A frequently used pages is often the oldest, so it will be repeatedly pages out by first in first out. Simple to implement. It requires only a pointer that circles through the page frame of the process. These are the example of first in first out page replacement, in which as per your string you are going to putting that frames into your frames. B-lead is anomaly, that is first in first out replacement, manifest anomaly. More frames, more page faults. It is also called first in first out. Visually on increasing the number of frames allocated to a process virtual memory, the process execution is faster because a favor page fault occurs. So sometimes the reverse happens, that is the execution time increases even when more frames are allocated to the process. LRU process replaces the page that has not been referenced for the longest time. By the principle of locality, this should be the page least likely to be referenced in the near future. Performs nearly as well as the optimal policy. These are the reference string and these are the flow. In what manner way these recently used pages are put into your page frames. Least recently used, that is LRU algorithm reference T. That is some of example. Hit page fault. Comparison, that is first in first out LRU. LRU recognize that page 2 and 5 are referenced more frequently than other, but first in first out does not. And last one is that is your optimal page replacement algorithm, that select for replacement the page that will not be used for longest period of time. Impossible to implement, that is needed to know the future but serves as a standard to compare with the other algorithm we shall study. These are the optimal page replacement example. Same way for frame example, 6 page fault. How do you know future use as like that? Now next new point, that is what is meant by thrashing. If process does not have enough page, the page fault rate at very high. So low CPU utilization, operating system thinks it needs increased multi-programming. It adds another process to system. So the thrashing is when a process is busy swapping page in and out. That is degree of multi-program CPU utilization. Working set. How much memory does the process need in order to make a reasonable progress? Its working set. Only run process whole memory requirement can be satisfied. Page fault frequency. Page fault frequency is represented through page fault and instructions executed. It rises above threshold. Process need more memory, that is not enough memory on the system, swap out. So page fault frequency sink below threshold, memory can be taken away. So in this way unit 5, that is memory management of system program operating system, is completed here. So thank you so much.